This is the chat session for MGF 1107. This is chat session on sections 5.3 and 5.4. Chat session topics: rational and irrational numbers. Now, what is a rational number? A rational number consists of all the numbers that can be written as the ratio of two integers or already is written as the ratio of two integers. For example, 3/4 is a rational number. 0.12 can be written as 12 over 100, so 0.12 is a rational number. 3 1/5 is a rational number because that can be written as 16 over 5. -6 can be written as -12 over 2. So -6 is a rational number. Also, a repeating non-terminating decimal is a rational number. So like 0.7777 ... that can be written as 7 over 9. So any non-terminating but repeating decimal can be written as the ratio of two integers. Now, just like people can be thought of as rational or irrational. Rational meaning that in a position, their behavior is predictable, but irrational in a situation, their behavior is unpredictable. Well, in a rational number, the digits are predictable, such as 0.7777 ... we know what the next digit is. But an irrational number, digits are not predictable. There's no pattern. We cannot predict the next digit. So irrational number consists of those numbers that cannot be written as the ratio of two integers. For example, suppose we have 0.3417 ... We have no idea what the next digit is. There's no pattern, no repetition. That's an irrational number. Another irrational number is the number pi. It starts off as 3.14, but then continues on forever and ever, no repetition. Another one is square root of 5. If we type in square root of 5 on the calculator, we'll get an approximate value for square root of 5, but again, the digits go on forever and do not repeat. These are all examples of irrational number. Now, what do we mean by reduced to lowest terms. Reduced to lowest terms means when numerator and denominator have no common factor or divisor other than 1. So for instance, 4/5 or 3/4 is reduced to lowest terms because 3 and 4 only share a common divisor of 1. Now, let's talk about fundamental principle of rational numbers, and we're going to go on to the next page for this one. Fundamental principle of rational numbers. If A divided by B is a rational number and C is any number other than 0, then we can say that A times C equals A and A times B and B times C equals B. The rational numbers A over B and A times C over B times C are called equivalent fractions. For example, 4/5 and 8/10 are equivalent fractions since 4 times 2 equals 8 and 5 times 2 gives us 10. To reduce a rational number to its lowest terms, we divide both the numerator and the denominator by their greatest common factor. So, for instance, if we have 16 divided by 48, we could divide both numerator and denominator by 16, and we would get 1/3. Mixed number. A mixed number is the sum of an integer and a rational number. So, for example, if we have 6 and 2/3, that's a mixed number, whereas an improper fraction is where the numerator is greater than the denominator. So if we have the fraction 7/5. Now some books will say when the numerator is also equal to the denominator. This particular book just talks about numerator greater than denominator. Now we're going to move on and talk about converting a positive mixed number to an improper fraction. Converting a positive mixed number to an improper fraction. So, for example, if we have 6 and 2/3, we can find the improper fraction by going 3 times 6 and adding the numerator 2 and keeping this all over the original denominator of 3. And this gives us 20/3. So we multiplied denominator 3 times the integer 6 and added the numerator 2 and put this all over the original denominator 3. Now, suppose we're converting an improper fraction to a mixed number. Let's take a look at an example. Suppose we have the fraction 11/3. We're going to take the denominator 3. We'll divide it into the numerator 11. And 3 divides into 11 3 times. 3 times 3 is 9. Subtract 11 minus 9. We're left with a remainder of 2. We put the remainder 2 over the divisor 3. And so what we get is the mixed number 3 and 2/3. And we just converted an improper fraction into a mixed number. Now, we have what are called terminating decimals and non-terminating decimals. Terminating decimals would be where the digits stop. So if we have 4/5, that would give us 0.8. So 0.8 would be considered a terminating decimal because the digits stop. But if we have a repeating decimal, That would be like 0.2222 dot dot dot. The digits do not stop and they repeat. This can also be written as 0.2 with a bar over it. Meaning exactly the same thing. And then we have the non-terminating decimals. That are also repeating decimals, but they can also be where there is no pattern to them. So this never stops. For a non-terminating decimal. Now, suppose you're asked to express decimals as quotients of two integers. This gets into thinking about decimal places. So like here's our decimal point. And then we have place values. So the first place to the right of the decimal point is tenths. Then we have hundredths. Then we have thousands. And then we have 10,000s. We keep dividing by 10 and get additional place values. So for example, 0.4 is the same as 4/10. 0.37 is the same as 37/100. The denominator is the place for the furthest to the right digit. So 0.4 stopped in the tenths place. 0.37 stopped in the hundredths place. 0.041 stops in the thousandths place. So that becomes 41/1000. Okay, now let's talk about multiplying rational numbers. Multiplying rational numbers. An example of this would be if we have A times C, we get AC over B times D, which gives us BD. So we multiply numerators together and we multiply denominators together. Hence, for example, we would have 4 times -1 which would give us -4 over 5 times 3, which gives us 15. So we multiply numerators together, we multiply denominators together. Now dividing rational numbers, this is where if we have A divided by C, this becomes A times D, which gives us AD, because what we're going to be doing is taking the reciprocal of the second fraction. Now, let's take a look at an example. Suppose in the example we have 4 sevenths divided by 5 ninths. This will give us, we'll have 4 times 9, which gives us 36. And that was 4 sevenths, and we're dividing by 5 ninths, which gives us 4 sevenths times 9 fifths, which gives us 36 over 35. Now, adding and subtracting rational numbers. If we end up having the same denominator, we just add the numerators. So adding and subtracting rational numbers. So if we adding with like denominators, keep common denominator, add numerators, and reduce answer if possible. But if we are adding with unlike denominators, we have to find the lowest common denominator. Then we find equivalent fractions using the lowest common denominator. Then we keep the lowest common denominator as the denominator for the answer. We add numerators and also reduce answer if possible. So they're very similar once you find yourself with a common denominator. Now, suppose you're subtracting rational numbers. Subtracting with like denominators. We keep common denominator and subtract numerators unless you need to borrow, and reduce answer if possible. Now, what if you need to borrow? Let's take a look at an example of where you need to borrow. Suppose you have 4 and 5 ninths, and you are subtracting two and 11 twelfths. Wait a minute, let's have it so it's 11. Let's have it be 7 ninths, because we're talking about with a common denominator right now. Okay, we can't take 7 from 5, but what we're going to do is we're going to borrow 1 from the 4, and that's going to leave us with 3. And then we have 9 ninths, because that's equal to the 1 that we borrowed. And we're adding to that 5 ninths that was already there. And that gives us 3 and 14 ninths. And now we can subtract our 2 and 7 ninths, because the top fraction has a bigger numerator than the bottom fraction. We keep our common denominator of 9. 14 minus 7 is 7. And 3 minus 2 is 1. And we just subtracted where we needed to borrow. Now, suppose that we are subtracting with unlike denominators. Okay, first you need to find the lowest common denominator and then you need to find equivalent fractions using the lowest common denominator, then subtract numerators and borrow if needed, and reduce answer if possible. Always need to reduce that answer if possible. Now, let's talk about density of rational numbers. If R and T are rational numbers with R less than T, then there is a rational number S that has R is less than S is less than T. For example, find rational number halfway between 1/4 and 1/2. Okay, step 1 is add 1/4 and 1/2, and we get 3/4. Step 2 is divide the sum by 2. So if we take 3/4 divided by 2/1, we get 3/8. The number 3/8 is halfway between 1/4 and 1/2. So by dividing by 2, we get halfway between the two numbers. Now, let's talk about radicals. Okay, the symbol that I'm drawing is referred to as a radical sign. And if we put something inside that radical, say I put in the number 9, the number 9 is called a radicand because that is the number inside the radical number. Now, and remember, that's read as the square root of 9 and is asking for what number times itself equals 9. Now we're going to talk about what is the set of irrational numbers. And we talked about those a while back, where those are numbers that cannot be written as the ratio of two integers. Set of irrational numbers and this is the set of numbers whose decimal representations are neither terminating nor repeating. Now let's move on to the next screen and we're going to talk about something called golden ratio. This is where 1.61821 is, and that's the same as saying square root of 5 plus 1 to 2 is the golden ratio. Viewed as the most pleasing rectangle when this ratio represented the length divided when the width when the length is divided by the width. United Nations building in New York City follows the golden ratio, and the ratio of the length to width matches this, the 1.61821. Now, principal square root is the positive square root of a number and is written as square root of n. No negative sign outside in front of the radical. Now, not all square roots are irrational. For example, square root of 16 is 4. But if I say square root of 7, that would be irrational. So it's all about whether it terminates or it goes on and does not repeat. Now, product rule for square roots. If we take the square root of A times the square root of B, they've both got to be square root, we get the square root of the product AB. And we are expected to, if we can take the square root of the number, to simplify it. But they both have to be square roots for us to apply this product rule. Now, dividing square roots, again, they both have to be square root. So, if we have the square root of A over the square root of B, that's equal to the square root of the fraction A over B. So these two expressions are equal to each other. The quotient of two square roots is the square root of the quotient. Now, adding and subtracting square roots. If we have a times the square root of c added to b times the square root of c, this will be equal to, we add a and b together, and that answer gets multiplied times the square root of c. But if we are subtracting a square root of c, subtract b square root of c, we first subtract a minus b, and take that answer and multiply it times the square root of c. Now, we're going to talk about rationalizing denominator. That's where we end up making the denominator a rational number. And this is called rationalizing the denominator. So if we have square root in the denominator, let's take a look at an example. Suppose we have 11 over the square root of 5. We have a radical in the denominator. Your final answer cannot have a radical in the denominator. So what we do is we take our starting fraction, 11 over the square root of 5, and multiply both numerator and denominator by the radical in the denominator, which is square root of 5. Now, 11 and 5 are not both under the radical sign. So when we show that they're being multiplied, we just write them close together and write 11 square root of 5. In the denominator, we have square root of 5 times square root of 5, which gives us square root of 25, because they can be multiplied since they're both under the square root sign. And our final step is to simplify that denominator, because then we're asking ourselves what number times itself equals 25, and the answer is 5. And we have now rationalized the denominator because we now have a rational number in the denominator. Now, other roots besides square roots. Other roots. And you may have seen these in your prior algebra classes. One of the other roots we talk about is cube root. Another root is fourth root. Another root is fifth root. There's an infinite number of roots. But cube root is asking for what number times itself, written down 3 times and multiplied, equals that number. So the cube root of 8 would be 2, because 2 written down 3 times and multiplied gives you 8. Whereas the fourth root of 16 would equal 2, because 2 written down 4 times and multiplied would give us 16. And the fifth root of 32 would equal 2 because 2 written down 5 times and multiplied would give us 32. But these are examples of other roots. This concludes this chat session. If you have any questions, please don't hesitate to email me or call me, and I'll be very glad to assist you. I wish you a great week, and please let me know how I can assist you.